In this problem, we are given a continuous beam ABC which carries a uniform load of 5 kN per meter from A to B and a concentrated load of 20 kN at the midspan of BC. The beam is simply supported at A, B, and C, and span AB is 10 meters while that of BC is 8 meters. We are tasked to calculate the reaction at B. And to solve this problem a lot easier, given an indeterminate beam which is a continuous span, we will utilize the 3-moment equation. So considering span A, B, and C, we can formulate our 3-moment equation that is given by the expression m sub A times the length of the beam on the left side of B, let's call this L sub 1, plus twice the product of m sub B times L sub 1 plus L sub 2, that is the length of the beam on the right side of B, plus m sub C times L sub 2, plus the moment factor on the left side of B, plus the moment factor on the right side of B, all equal to 6EI times H sub 1 over L1 plus H sub 3 over L2. Now since the deflection at the supports are all equal to 0, therefore this entire expression here will become equal to 0. Now let's plug in the known values. We have the moment at A that is just equal to 0 because the moment at the free end of a simply supported span that is just equal to 0, and also m sub c. We have the length of the beam on the left side of B that is just equal to 10 meters, and the length of the beam on the right side that is equals 8 meters. And for the moment factor on the left side of B, that is just a uniform load with a magnitude of 5 kN per meter, is given by a formula WL cubed over 4. So let's plug in the known value. We have 5 times the length of 10 meters cubed divided by 4, that is equals 1250. And for the moment factor on the right, that is a point load at the midspan, that is given by the formula PL squared times 3 over 8. Which is equal to 480. Simplifying this expression, we will get 0 plus 2 times m sub b times 10 plus 8, that is just equal to 36 m sub b, plus 0 plus the moment factor of 1250 plus 480 equal to 0. We will get the value for m sub b that is just equal to negative 48.0556 kilonewton meters. Let's proceed solving for the other reaction. Let's say reaction C by cutting the segment of the beam BC. So by cutting that segment, we expose the internal shear and moment at point B. Since the moment here is negative, therefore it will act in the counterclockwise direction. And let's assume the shear is going in the upward direction. We have R sub C due to the roller support at C and a 20 kN force that is going downward. And to solve for the reaction at C, we take summation moment at point B equal to 0, considering counterclockwise to be positive. So we have R sub C times a moment distance of 8 meters that is going in the counterclockwise hand, so it's positive, minus the 20 kN force that would induce a clockwise moment, so it's negative, and then plus the counterclockwise moment of 48.0556 kN meters, all equal to 0. We can solve for RB, that is equal to 3.99, or approximately equal to 4 kilonewtons. Now to solve for the reaction at B, we consider the whole beam. Let's call this reaction R sub B. And by taking summation moment at point A equal to 0, considering counterclockwise to be positive, we can solve for RB. We have the moment induced by the uniform load that is equal to 5 times 10 meters to get the resultant, multiplied by the moment arm distance of 5 meters. And the sign convention here, since counterclockwise is positive, and this uniform load would induce a clockwise moment, so it's negative. Minus the moment induced by the 20 kilonewton force times the moment arm distance of 14 meters, plus the moment induced by R sub B, that would induce a counterclockwise moment, so it's positive, times the moment arm distance of 10 meters, plus R sub C of 4 kilonewtons times the moment arm distance of 18 meters, all equal to 0. We can solve for R sub B, that is equal to we get R sub B that is equals 45.8 kilonewtons. And that is our final answer, which is letter C.